Welcome back to Gophercises. In this exercise, what we're going to be doing is creating a deck of cards, and we're going to create that as a package that developers can grab. They can use it to build decks, they can filter out certain cards, they can add jokers to their deck. So it'll give us some pretty generic functionality that you might want with a deck of cards. It's also going to define some common things like ranks, such as like an ace, one or an ace, a two, a three, all the different cards you'll see in a typical deck of cards, as well as their suits. So hearts, spades, diamonds, clubs. So in the process of doing this, we're going to be adding some different functionality to this package that might not make a lot of sense if you haven't checked out what the next exercise is going to be. So then I'll try to explain this as I go, just so you understand why I'm adding these things. But the next exercise is going to be building a blackjack game using this package that we create here. So the goal is to, just create a relatively generic deck of cards API. And then the next exercise will be build a blackjack game. And then the follow-up exercise after that will be add a little bit of AI to it, which is going to be fairly simple. Blackjack AI, the logic for a dealer is pretty standard in blackjack and it's not too complicated. But we'll at least show you a couple different ways to alter that functionality and maybe give us like a beginner AI and a full dealer AI, so you have different odds of winning the game. So in this exercise, we're going to be using a couple different things specifically. I wanted to cover some specific topics, so I intentionally tried to shape this package so that it would sort of match those. The first is the sort package. I wanted us to see how to sort slices and do things like that. And I don't know if we covered it in another exercise, I don't remember off the top of my head, but it's something that you'll end up needing a fairly good bit in your code in my experience. Sorting things is pretty handy at times, so it's nice to know how it works. Next is shuffling with permutations. You probably won't use this one as often, but I think it's something that's interesting to look at. It's kind of cool to look at. And I'm hoping to also get some time to sort of show you how to test code that uses something like this. A lot of times people have random things in their code and they won't know how to test it correctly. So hopefully we'll be able to write some code and look at how we could actually test, doing random things in our code and do it in a deterministic way that isn't, potentially going to fail or maybe not be a useful test every single time we run it. The next thing is go generate. We're going to be looking at how to generate code using the stringer, which is this. Let me open it up. Stringer is this command that's part of the Golang tools. It's relatively simple. It just allows you to sort of make some constants print out a little bit nicer. And we're going to use that. And then we're also going to practice with some functional options. So I'm going to let you sort of go through the rest of this. You read through the description here, see what you're supposed to be doing. I've described roughly what we're doing. A lot of this is going to, in detail say, here are the things you should add. Here's sort of all the different pieces you want to be adding to this. And again, a lot of this is based on the fact that I know what we're going to be doing long-term with this. So I want to, sort of set you up for that. Now, there are a couple options down here that we'll be adding that we won't use in our blackjack game, but I know that other games, if we end up using this package for other future exercises, could use, such as filtering out twos and threes. So if you're playing a game like 500 bid or something like that, a lot of times you'll filter out specific cards to, get the deck a little bit smaller. So you don't play with maybe twos and threes. You only play with fours and up or something. So having a generic way to filter out cards can be pretty useful. And the same goes for all these. Like, we'll have an option to add jokers. Some games don't use jokers, obviously, like our blackjack game won't. But it's a generic enough thing that I think it's useful to have in the deck of cards that we set up and have it be aware of jokers and that sort of stuff so that it can sort of, go from there. And then finally, the bonus stuff. Normally I'd have bonus exercises that are, go code something, do something. What I want to do for the bonus here is I want to add proper documentation to our entire package and then to see how it works with GoDoc. I don't think I've done that with a previous pack or your previous exercise. So I think it's interesting to see how GoDoc can be run locally, how you can read the docs from your source code, and why it's important to add proper documentation to code that you're going to be sharing with others. And I didn't talk about it as much in some of the other exercises because most of the time we were building really simple, binaries that we'd be running. Whereas in this case, we're actually creating a package, so it's intended to be used by other developers. And as a result, it's important to make sure we have good documentation that sort of shows, how they can use the different things, what they're supposed to be used for. So we're going to look at that as the bonus part of this. The first thing we're going to start with is just declaring the card type that we're going to be using. So I'm going to go ahead and jump over to our code here. And we're going to go ahead and create, we'll call this card.go. And this is going to be inside of the package deck. And what we want to do is define the card type that users are going to be using whenever they get a deck of cards. So I think the card type is more important to start with than anything else because it's kind of the building block we're going to be working with. So I'd go ahead and start with, just a struct for this. And then we got to think about what goes inside of here. So what are we going to put inside of this card type that allows users to, figure out what a card is, but it's not so specific that it's, specific to a single game and, is therefore not useful to everybody. So the first two things that I think of are, suits and ranks. So if we go, let me see if I can find playing card. If we can bring up a playing card image, you'll see here looking at these that a lot of these have a suit. So hearts, hearts, diamonds, spades, and clubs. And then they'll have a value, or what's typically called a rank, which would be ace, 2, 3, 4, all the way up to 8, 9, 10, and then jack, queen, king. So you can see the jack, queen, king here. Now, there are a few exceptions to this. There are things like jokers, which technically don't really have a suit to my knowledge. So, you might want to think about that there's something there. There's also colors. So some decks will have hearts and diamonds are red. Spades and clubs are black, but then you also see that some decks just seem to throw every color as every suit is a different color. I think the most standard is that hearts and diamonds are red, spades and clubs are black, but I don't know that the coloring is super important to put in our code, mostly because, well, you could derive it. It is something you can derive from the suits itself, so we could leave that up to other people. I think the first version of this, that's what I'm going to do. But that's something you might consider in future versions of the API. Maybe you want to add a color so that it's easier for developers to figure out what color a card is. So we know that we need something here for a suit, and we need something here for a rank. And these two would give us a rough idea of what a card is. So to do this, we could say a suit is maybe an integer, and then we could just define it as 0, 1, 2, 3. So 0 might map to spades, 1 to diamonds, 2 to clubs, and 3 to hearts. That's one way we could approach this, but I don't know that the integer is that clear as to what it means. So when a developer sees it, he's not going to really think, oh, that's clearly, just a suit that's meant to be like spades, hearts, or something. So in this case, it probably makes sense to define our own type. So we're going to call this the suit type, and we're going to export it because we want developers to be able to use it. And we know there aren't going to be too many of these, so I'm going to make this a uint8. Basically, this is, it's not going to be too many possible values for this. And I'm doing it mostly just because I don't see a reason to use a full, a regular integer here when we know that it's going to be a relatively small data set. Now, if you really wanted, you could use an integer. I don't think it's going to be a major issue, but just something to keep in mind. Okay, so now we need to define what suits there are. Since there's a very limited number of suits, I think it's important to go ahead and make these a constant. So we're going to go ahead and say spade, diamond, club, and heart. And then we need to define the type here. So I'm going to say this is a suit, and I'm going to use the iota, if I could remember to type it. And what the iota does is inside of this constant block, whenever you start it, this will get a value of 0. And then every constant afterwards will get an incremented value. So spade will be 0, diamond will be 1, club will be 2, and heart, if I can capitalize that, will be 3. Now we're also going to need another suit, and this one's going to be a little bit funny. Joker is not technically a suit, but I said before when we were looking at all these cards, jokers are typically suitless, and we can still give them ranks to sort of differentiate between different jokers if we want down the road. Those ranks might not be used for, values, but once somebody sees that it is a joker, they could say, okay, this is the first joker, the second joker, if you do need to differentiate. I think most games don't really differentiate between the jokers, so it's not something I get too worried about here. So this gives us all of our suits. I think the next thing I would do is just go ahead and add the suit here to the card type, and we should, have this suit available to us. So we're going to do the same thing roughly with the ranks. So I'm going to go ahead up here and I'm going to say type rank uint8. And this is where you might not want to do this. It's kind of up to you. Creating all the constants for ranks is kind of cumbersome because there's 13 of them. So you don't have to do it, I don't think necessarily, but I like to do it because it makes it easier for developers. whenever they're writing their code, they can actually say, if deck.ace, if that's what the rank is for a card, it can very easily sort of figure out, what a card is, and it makes the code easier to read rather than, looking at numeric values. So what I want to do here is the same thing as above. I'm going to have ace rank iota, or equals iota. And then down here, I'm going to go with a 2. And I don't need all this other stuff now. So it's just going to infer that it's a rank type, and it's going to increment the value because of the iota here. And then from there, I can just sort of copy all these and go 3, 4, queen, and then king. Okay, so that's all of them. But before we move on, there's one thing I want to point out. When it comes to suits, they don't really have, the number that is assigned to them isn't really important, because suits don't really have a numeric value. Now, I intentionally put these in a certain order, which we'll look at later, and that is the order that cards are typically sorted in a brand new deck. Typically in a brand new deck, you would see ace, 2, 3, 4, 5, all the way up to king in spades, and then the next set would be all the diamonds, then all the clubs, and all the hearts. So I intentionally put these in this order here, so that later when we go to sort, that'll be a little bit easier. But down here, when we're looking at these, ace is going to get the value of 0, 2 is going to get the value of 1, and it's kind of like an index for an array. It's all going to be 0 based. Well, it might be a little bit easier down the road if we actually had the ace equal to 1, the 2 equal to 2, the 3 equal to 3, and so on, because this makes a lot more sense, especially as people start to build out scoring systems, where in a lot of games, a 2 will actually have a point value of 2, a 3 will actually have a point value of 3. And while cards like an ace might have special point values, they're kind of the exception. They're not the general rule in a lot of those games. So what we're going to do for that is we're actually going to take this ace, move it to a new line, and we're going to put an underscore here. So we're going to assign the underscore to the iota first, so it'll get 0. And we skip the 0 and make 1, 2, 3. So all these are actually going to have values that correspond to, what they actually are. So the next thing we're going to do from here is just go to the cards, add the rank to it. And then from here, what I want to do is look at the go generate and the stringer command. We're going to use it to, basically what we want to do is we want to make it easier to print out all of these different types. So if you're looking at them, clearly we don't want to be printing out zeros, but at some point we might need to print out these cards. Or sorry, not zeros. We don't want to print out numbers. We probably don't want to print out, 1 and then 0 for the suit. That's not really clear to end users what that is. So when we go to print out a card, it might be nice to be able to print out something like func card string. So when we have the string function, which can be used to, whenever it gets printed out in a print line or something like that, it might be nice to return something like ace of hearts or maybe jack of spades, something like this. So we want to go ahead and find a way to make these suits a little bit easier to print out. We've already written out all these constants that represent what these suits actually are. So we can take advantage of that and use the stringer pack or command to go ahead and do that. So what we're going to do is, let me grab the link from my notes. We're going to be using this command stringer. And if you read through here, it'll tell you basically everything you need to know about using it. I will say the first thing we have to do is go get it. So if you don't already have it, go get it. And then you can use stringer, and you'll see here that there's a bunch of different commands you can use, or not a bunch, there's a couple different commands you can use for it, but we don't actually need to manually run this. What we're going to do is come down here, and you'll see that typically this process will be run using go generate like this. So we can actually set up a generate comment at the top of our source code that will tell go generate the command what to run, stringer, and what flags to give it. And it'll go ahead and run that, and with that being run, it will create some source files that make it easier for us to create the string method that you're seeing here. So this one I think just makes more sense if you see it in action. So I'm going to go ahead and just add this. And then here I'm going to say the type. So the type is the constant types that we're trying to create the stringer for. So we want one for suit, and we want another one for rank. And these can be comma separated. Okay, so I've saved my source. Now I'm going to go generate. And you'll see here that suitstring.go was created. So I'm going to go ahead and open that up. Now this is a generated source file. You'd still check it into your source control and keep it with your builds and all of that stuff. but you generally wouldn't be editing this. You wouldn't be touching it or doing any manual edits. So what's happening here is the generated code is going through all of our source code, and the stringer package is going through or command, sorry, is going through our source code and our constants, and it's generating the string functions that use this string here, and then use the rank index. It uses both of these in order to, excuse me, uses both of those in order to print out a rank. So you see it here, that's what's going to be happening. And if you pass in a rank that's higher than what it expects to be in this constants, list of constants, it'll print out rank with a parenthesis and then just, an integer value of it. So we can go ahead and see this in action. We could write we could write just a main.go to run this, but I think this is actually an easy thing to add a test for. So we're going to go ahead and finish this first, and then we'll add a test to see this all working. So what I want to do is I want to say if c.suit is not equal to joker, because jokers we're going to print out very different. So I'm going to say if it's not a joker, if it is a joker is what I want here. So jokers are the unique case where we just return joker. Otherwise, and you will see that this is c.suit.string, so we can actually return that, because we now have that suit.string method that you're seeing right here. So we're going to return that just instead of like the hard-coded joker, because down the road, if we ever change this for some reason, or maybe we update the string function to, I don't know, have different languages we can provide with flags or something like that, it can be changed that way. Otherwise, we're going to return fump.sprintf, and we're going to say %f or %s of %s, and then put an s at the end. So this first %s is going to be things like ace, 2, jack. This last part is going to be the suit, so like heart, spade, and then the s at the end is just to make it plural. And we got lucky here that spades, diamonds, clubs, hearts, you can just add an s to all these and make them plural, so we don't have to do anything fancy to try to make this plural. So we need c.rank and c.suit. And we could explicitly call, let me see what's going on here. All right, so we need to do string here, and that's what I was just about to talk about. We could explicitly call these string function or methods in this case to make sure that it's passing the correct strings in there. And that'll go ahead and just simplify this a little bit for us. Now we want to see this whole string method in action. I think the best way to do this is with an example test. So we're going to go ahead and create Atom card test.go. And then inside of this, we're going to say package deck. I don't see any reason to make this an external package. We could, but I'm not going to do that for now. And I'm going to add example card as a function. And here we're going to go ahead and say print line. We're going to print out a card. We'll give it a rank of ace and a suit of heart. And then at the end, we want to go ahead and tell it what output we expected. So this is how you turn an example into a test case as well. As you go ahead and write the example up top, you print out whatever you want to print out. And then at the bottom, you put this output comment. And then on every line, you just put all the output you expected in the comments. And when you run go test, it'll compare it to all that output to make sure you're getting the right output. So we're going to say ace of hearts is what we're expecting here. So we're going to go test. And this looks like it's working. So let's go ahead and just verify that. I'm just going to add some random stuff to the end of that. And you'll see here that now that we've added random stuff, the test fails. It prints out, prints out ace of hearts, but it thinks we want ace of hearts 9090. So if we delete this, go back to what we were, our code should work again. Okay, so this wouldn't be much of a test if we just printed out one card. So let's go ahead and print out many different cards just to make sure they all work. And let's just give them different ranks and different suits. So let's just, for the last one, I want to test a joker as well. I want to make sure that one's working because it's a special use case. And we shouldn't need a set of rank for it at all. So I'm going to go ahead and test without setting any rank. And now for the suits, we want spade, diamond, and club. So we're expecting this to be jokers at the end. We're expecting a 2, a 9, and a jack. And then we want club, diamond, and this will be a spade. Oh, these are all plural. Okay, so I've saved this. Now we're going to go test it. And it looks like it's working still. Again, if I want to just add some random strings to this to verify that it is working, I don't think this is really necessary to double check, but it is working for sure. So we'll save that. We'll go back to our code. And that should be testing most of this. It's not testing everything perfectly, but I think it's a reasonable test for what we have here. So that's everything for setting up the card type. I don't think we need anything more than this. Looking at all the code and knowing how we're going to be using this, I think this is plenty to get started. And down the road, we could always add to it if we do find specific needs for things. But for now, I think this is plenty. These next few videos are going to be relatively smaller snippets of code, but each one we're going to add either an option or some sort of functionality to this package that I think would be useful on a, in a more generic level for everybody who uses a deck of cards. So the first is the most obvious and most useful thing. We need a way to create a deck of cards. So we need a new function that will return a slice of cards. You can see here that I'm using a slice of cards instead of a custom type. So we could add like a deck type, something like this type deck, and it's really just a slice of cards. And then we could add custom methods to this. One of the big benefits you're going to see from that is that you could add, you can make sure the deck implements maybe the sort function or sort interface, which is golang sort. Let me go ahead here and look for it. There it is. You can get the sort interface, which would basically be, make it easier to sort things down the road. They wouldn't need any custom functions, but I don't necessarily think that this is such a big deal. We can actually just implement a single less function later on, and that'll enable us to, to make this a default sort viable. But I also don't like it because everybody sorts decks of cards differently. Depending on the game you're playing, the way you want to sort the cards could vary. So for instance, if you're playing, a game where suits matter, you definitely want to sort the cards, based on their suits. But you might have something like spades where a jack of, the trump color or something it has a different value than, say, a jack traditionally would in a deck of cards. So I don't think having it built into the type is that useful here. I think it makes more sense to just go ahead and provide a function or a closure that'll make it easier to sort, but doesn't sort of imply that there's only one way to sort these cards. So inside of here, we want to create a deck of cards, and then we want to return them at some point. So from here, we want to go ahead and fill them up. And the best way, in my opinion, to do this is to just go ahead and build the deck as if it was a brand new deck. And we've actually set up all of our constants up here to make that a little bit easier. But first, I want to add a couple things to help us with that. So what I'd like to do in pseudocode is something like for each suit. And then inside of that, I'd like to do for each rank. And then I'd like to do add card, suit rank, 2 cards. So that's roughly what I'd like to do in pseudocode. So to make this work, I need to get a list of all the suits. Well, since there's only 4 of them, and the order here does matter, and I think it's kind of, it's just nice to see this visually, I think it's okay in this case to create an array. This is actually an array, it's not a slice like a lot of the other things we're going to be using whenever we write Go code. And I'm doing that because I know this is going to have a fixed size. It's actually going to get determined, the size will be determined at compile time. But I know it's going to have a fixed size. I know we don't want to add things to it. I really don't even want to edit this. If I could make it a constant, I would, but it's not going to be constant because it's an array. So then here, we're going to go ahead and put these in order. So we're going to have spade, diamond, club, heart. And one of the reasons I like doing this is because I don't want to create, like say this is what the max suit value is, this is what the min value is, because that would be a little bit weird with the Joker. It's going to be above the max value if we set the max value to heart. So we don't really want to do that. But I think here it sort of makes it clear that these are the actual suits. Joker, we could put something like this is a special case. All right, so we have our suits. The next thing I want to do is give us a way to look at all of the ranks. Now, in this case, we could create another array. I don't think that's what I want to do here. One, it's just annoying to manage. With four, only four up here, we can set the order. Maybe we want to change the ordering of this so that diamonds come first for some reason. We realize we made a bug. But down here, when we look at the rank, first off, we know these are in the perfect order because, they're all numeric values basically mapped to them. But on top of that, there's just so many that it's just, we don't really want to write that out. So what I'm going to do is I'm going to put a min rank and I'm going to put a max rank. And I think this is useful in the sense that it allows us to iterate over all these rank constants, but it's also not, it's not making us write a big array of all these like we are up here with the suit. And we could do that with the suit as well. I just think that for the suits, it's okay just to do it this way. It's a little bit clearer what you mean by it. And it's also just, there's only 4 here, and having integer values or whatever, or iterating over them within a for loop like that is going to be a little bit weirder. Okay, so down here to our code. For each suit in the range of suits, so that'll cover our suit loop. And then we want to go ahead and say for each rank. So I'm going to say for rank is min rank. Rank is less than or equal to max rank. And I do want to mention this does need to be less than equal to because the max rank is the king and we want to use that rank. Rank plus plus. And suit declared not used, that's fine. Okay, so inside of here, we want to create the cards. So we're going to say cards equals append cards, and then we're going to create a new card. So I'm going to have a suit of suit and a rank of rank. And that should be it then. This will create a new deck of cards for us. If we wanted to test it, we could have a couple quick tests. I guess we could do something like func test new. And what do we want to do here? I think I didn't want to focus on testing too much in this video. I want to focus mostly on the deck of cards. So I'll keep this simple. I'll create a new deck of cards. And I'm going to say if the length of the cards is not equal to 52, which is the normal size of a deck of cards, this should be 13 times 4, which you can see here is 52. So if the length of cards is not equal to 13 times 4, we might want to put something. We can put 13 ranks times 4 suits. Here we do t.error. You might want to put something like not enough or too many, but wrong number of cards in the deck, in a new deck. And then if you wanted to add more to that, you could. I think that's fine. It's a relatively simple test. And then we can go test it. And it appears to be testing. And if we change one of these to say 12, you'll see here that it's failing and it's telling us there's a wrong number of cards in a new deck. So again, not a perfect test, but I think it's reasonably fine for what we're looking to do. I don't want to iterate through and make sure all the different suits and ranks are there. I guess you could put a couple, if you want to test on your own, you could put a couple checks here. Make sure the first 13 cards are all of one suit. Make sure the next 13 are a different suit. Make sure all 4 suits are present. There's a bunch of different things you can test depending on what you think is important to test with your code. Okay, I'm going to delete these comments. And that should be it for this part. All right, in the next part of the video, or part of this exercise, we're going to look at adding options to this, which we don't really have a good way to do yet, but I'm going to show you how to do that in the first option, and then the rest of the options will just be implementing those. The next thing we want to do is add options to our, whenever we generate these decks of cards, we're going to have some options. We want to be able to add jokers to our decks. We want to be able to shuffle our decks. We want to be able to make sure they're sorted, maybe sort them by custom values. There's all sorts of things we might want to do. So what we're going to do now is look at how to add these options to the new function. Specifically, I want to be able to pass in any variable amount of options and have them all run properly. So to do this, one of the ways you could see people traditionally do this, especially in a lot of other languages, is you might create some type that is a struct. So new ops struct, and here you'd put in all sorts of things. Maybe you'd have an option for shuffle, which is a Boolean as to whether or not to shuffle, and a bunch of other things like that. The problem with this is that it's a little bit unclear. You almost need pointers for everything, so you can say, all right, it's either null or nil in this case. It's either nil value, or it has a value and it's true or false, or something like that with options. And I think we talked about this in a previous exercise when we looked at functional options. So what we're going to use instead are, what I just said, functional options. If you've never used them before, I'm almost positive I used them in an earlier exercise. I definitely also suggest checking out a talk by Dave Cheney. I think it's called First Class Functions or something like that. It's definitely worth finding and looking at. In it, he shows you how to use functional options as a way of providing options to a calculator, which is a really simple calculator in the new demonstration, but it's meant to sort of illustrate the point. So here we're going to do that same thing. We're going to take in options, which are a variadic parameter, which basically means we can pass in 0 or more of them. And an option is going to be a function that takes in a slice of cards and returns a slice of cards. Now, I'm not trying to modify the slice of cards inline here. I'm instead allowing my function to return a brand new slice. And the reason for that is that a lot of our functional options are going to be adding new cards to the deck or doing things like that. So we want to make sure they have the full, flexibility to be able to do that. If we had to modify this slice in line, well, then we wouldn't be able to add new cards to it. We'd be able to shuffle them around or sort them, but we couldn't actually add new cards. So that's why we're going to make it like this. So then to run these options, it's a simple for loop. For each option in the range of options, we want to say the cards are equal to the cards after running that option on them. And this will run all of our options for us. So now we want to see this in action. I think the easiest way to do this is with sorting. So specifically, we're going to create just a default sort option, and then we're going to add a second option, which is related. It's going to be a sort option that allows users to pass in a custom, comparison function. And it's going to be a little bit more confusing. I'm not really sure if it's worth keeping in here, but I will. Okay, so to do sorting, we need three things basically. The first is we need a way to get like an absolute rank for a card, or like, a ranking if we were to compare them, because right now we've got suits and ranks. How do we decide which card is better? Well, we could say if the ranks are different, here's our sorting order for ranks. Otherwise, if the ranks are the same, sort by the suit, or you could do the opposite of that. If the suits are the same, do the suit sorting first and otherwise do the ranks. And I think that would end up being, it would work, but I think it's a little bit easier to do something like func abs rank. And I'm not sure if this is the best name for this, but I'm going to go ahead and go with it. And what we could do here instead is return c.suit times max rank plus c.rank. And what this ends up being is something like, say we have a suit, which is the first suit, or index 1, or not index, the value 1 from the iotas up here. So we have a diamond. And then its max rank is the maximum rank here, which ends up being king, which will have a value of 13. So down here we say 1 times 13. And then let's say the current card we have is a 4 of diamonds. So its rank is going to be 4. What this ends up doing is 1 times 13 will make sure that the minimum value this suit can get is a 13, which means that every card in this suit will always end up having an absolute rank value that is greater than the spade suit, because it's going to have 0 times 13. So its base value here is always going to be 0. And then this last part where we add in the rank, this is just a nice little way to, give us all of the numbers for all of our cards in a nice sorted order. Now to make this work, we need to go ahead and cast these to integers, or convert them technically, I think. And from there, we have our absolute rank function. Now, I didn't export this because I don't think it's useful outside of our code. I don't think this is something we need to export to people, because we only use it internally for sorting. And, we might change things up later as to how we decide how to sort those. So it's nice just to keep that sort of hidden. All right, so next we want a way to sort these. So we want a function that allows us to, given a slice of cards, to create a less function. So a less function, if you're looking here at sort.slice in the sort package, is this function that takes in, sort.slice takes in a slice, and then it takes in this less function. So pretty much any of the sort functions like this are going to be very similar. They'll often take in a function that basically just says, I need to know, given two indices in the slice, is the first indice, the value at it, less than the value at the second index. So what we're going to do here is create a function less that takes in some cards, and it returns that function ij int bool, that less function. So it's going to return func ij int bool. And inside of this, what we're going to say is return abs rank of cards I, whether or not it's less than the absolute rank of cards j. And this is why we needed to create this less function that takes in the card slice. We need to actually be able to access the cards at each of these indices, which means we end up needing a closure here so that we have access to them. So with those two, we can add a function default sort, which takes in a slice of cards, and I want to make this cards plural, and it returns a slice of cards. And what we're going to do with this is sort.slice, that function we were just looking at. We'll pass in the cards and we'll pass in less with the cards, this less function we just created. And then we're going to return the sorted cards. And that's our default sort. So to use this in our code, it would end up being something like new default sort, and that would actually work. This default sort would get run because it is a function, so it works as one of these functional options. And we could actually, if you wanted to put this in here just to sort of see, you could add default sort here. Actually, we could do func test default sort. And we could say cards equals new default sort. If the cards at index 0 is not equal to card, I think the rank is supposed to be ace and the suit is supposed to be spade. Then we want a t.error, expected ace of spades as first card. Received. Card 0. And we got to figure out what I'm doing wrong here. Apparently I couldn't do that inline. I'm not really sure what I was doing wrong there, but that's fine. Okay, our tests are passing, but you'll see here if I do change this to say a heart, run it again, our tests are failing. Received ace of spades. And I think that's fine as far as sorting goes. You might want to check the last card or a couple cards in the middle, but I think this is, again, a simple enough test that we can keep it for now. Okay, so the next thing we want is a custom sort. So if the user wants to provide us with a custom sort as an option here for new, how do we do that? Well, if we look at default sort, it's a really good boilerplate for figuring this out. What pieces inside of here does the user have to provide us in order for us to, create this, change this part to make it dynamic? Well, this less function is pretty much the only part. As long as we have, this less function, whatever they want to replace that with, we can, allow them to pass in a custom sorting function. So we're going to say func sort, and this is going to take in that less function, which, if you see here, is a fairly long function definition. But that's what we want. It's going to be a function that takes in a slice of cards, and once it gets a slice of cards, it returns the less function here. So this is all one type. I know it looks pretty big, but it is one type. This is the function, sort of like the function parameters, and this is the return type from that function, which happens to be a function with its own parameters and return type. All right, so from there, we want to return a function which takes in a slice of cards and returns a slice of cards, because that's what this default sort is. It's a function that takes in a slice of cards and returns a slice, and that's what we need up here for our options whenever we call new. So that ends up being a pretty long line, but from here, basically it ends up being return func cards, card, and card like this. And then inside of this, we want to do sort.slice cards, less the one that they just passed in with the cards. Then we'll return the cards. And you can see that this part here looks almost identical to this stuff up here. We just end up using this less function that was passed into us. So this is one of those cases where writing the really simple default version can be very helpful because it gives you a good boilerplate to build the more generic version like this. Okay, I'm not going to write a test for that right now. If you wanted to test it, one of the ways you could test it is use this sort function with this less function, which is the same as default sort, but you're verifying that this sort function works correctly. And since we already know this is working, since it's being used with default sort, it really verifies that just the extra code that we add here is what's working correctly. So it would end up being something like test sort less. And, well, I mean, I guess we can keep it now that we've written it, and they're both passing. Okay, so that's it for sorting functions and sorting options. What we're going to do next is shuffling, which I'm going to show you how it works. I don't want to dive too much into it. We'll get to that there, I guess. So, if you want to jump into the shuffling, that's the next video. The shuffle option is going to be similar to what we just did. It's going to be a function that we're going to call it shuffle. It's going to take in a slice of cards, and it's going to return a slice of cards. For this one, we won't need any fancy closures or anything like that, like we were doing here. All we'll need to do is just figure out what the new order of the cards should be, create a slice that has the cards in that order, and then return it. So what I'm going to do is I'm going to start by just creating a new slice of cards, and it's going to have the length of the cards that were passed in here. Now, there are ways to shuffle inline without having to create a new slice. And technically they're more efficient in the sense that we don't have to allocate all that memory, but I'm going to go ahead and use this version because I think it's a little bit easier to understand. And I think that's important for, just doing exercises like this, is to make sure you understand the code perfectly and to not prematurely optimize things like this unless it is really necessary for some reason, like you have constrained environments or you're really just trying to clean up some bottlenecks. So what we want to do from here is we want to figure out a new permutation or a new order for the cards. So I'm going to go ahead to the rand package. And inside of this here random package, I'm going to go to this perm function. So what perm does is, given a number, for instance 3, it will return a new permutation that has all of the numbers in, between 0 and that number, not including that number. So what this really means in practical terms is if we call perm of, say, 5, so if we did rand.perm of 5, something like this, what would end up happening is this would return us with a slice that is something like 0, 1, 4, 2, 3, something like this. So the order of these numbers is going to be random. It's going to be a random permutation. So permutations are basically just saying we have all these numbers, just change the order of them, shuffle them around. So where this helps us with shuffling our deck of cards is that this won't be the actual order of our cards, but if we take that permutation, we can then say, all right, we can say the first one's supposed to be the card at whatever index it gave me. So the first card in our new deck should be the card at index 0. The next card should be the card at index 1. Well, those two happen to be in the original order, but, just pretend like it is still random shuffling, so, you never know. The third card is going to be whatever card was at the 4th index, and then the 4th card is whatever card was at the 2nd index, and so forth. So that's how we end up using these numbers, and this permutation becomes very handy, is that we can actually use it to, just put the cards where they're supposed to be. Now, if we wanted to do this, we want to make sure that we have some sort of source for generating our random numbers. Now, there's different ways you might want to go about doing this. For now, I think what I'm going to go ahead and do is just create a new random source, and we'll go with that. It's a little bit trickier to test that down the road, but we should be able to, change it up later if we want. So we're going to say R is going to be rand.new. I won't use a capital letter. And we're going to pass in a source, which is going to be time.now.unix. So what this is doing is rand.new will give you what's essentially a, let me look forward here. All right, this right here, it gives you a new source object, which is essentially something that has all of the methods in the random pack or all the functions in the random package. But instead of using the global source that's in the random package, it'll instead use the source that you gave it, the seed that you gave it, which ends up being nice because that means that you can make sure your seed is something different every time your code is run. So it actually is being a little bit more random then. And then from here, we're going to say for ij in the range of r.perm. And then for the number of items in a permutation, we want this to be the length of our cards so that we can actually get a random index for every single item in our list. And then what we're going to do here is we're going to say ret of I equals cards j. So cards is the original slice, j is the value in this permutation. So what we might want to say here is perm : equals like this, just to make it clear that this isn't happening every single iteration. And it's not, but just to make that clear. So j is the index inside of a permutation. So it's, it's not the index, it's the value inside the permutation. So before, when I said perm is equal to, if I can type, perm is equal to 0, 1, 4, 2, 3, and maybe it goes on, beyond that. J are these values inside of here. I, on the other hand, is the index of where we are inside of the permutation. So it's going to be 0, 1, 2, 3, 4. It's always increasing that way. So what we're saying is, as we go through the indices here, whatever value is in there is the index in the card slice that we want to get the card from. And then finally, we return ret once we're done with this. And this should be a good way to shuffle our cards. It's not perfect, but it's not like the best version you could ever have of a shuffle, but it should be functional enough for what we want to do. If you want to learn more about shuffling, I have an article here that I go into this in a little bit more detail. And I'm not just trying to plug my own stuff, but since this is something I've covered in a written article and sort of shown different ways to shuffle stuff, I don't want to go over it too much here. I think it'd be more useful to just go read the article if it's something that interests you. And if it doesn't interest you, then just use what we have and we're good. Okay, so next up is going to be jokers. The next thing we want is a jokers option. And for this, it's going to be a little bit more similar to the sort option here, where we're going to actually call a function and it's going to return the option function. So for shuffle and for default sort, you'll see that the way we'd end up calling these is something like new shuffle. We don't actually call the function because it already matches the definition of what we want. When it comes to jokers, it's going to be a function that looks like this. So it's going to be a function where you pass in the number of jokers you want to get into your deck, and then it returns you a function that takes in a slice of cards and returns a slice of cards. And the reason for this is that now we can do new jokers 3, and we have that option of saying how many jokers we want. We don't just have to call joker, we don't have to write a function that just adds one joker and just call it over and over again. That would be annoying to have to put something like joker, joker, joker. That just wouldn't be fun to code. So we're going to go ahead and make it so that you can call jokers and pass in the number that you want. Okay, so inside of this, we want to return a function, which, as I said, takes in a slice of cards and returns a slice of cards. And inside of this, what we're going to do is iterate from I is 0 to n. And we want to go ahead and just add jokers to the deck every single time. So we're going to say cards equals append cards, and then we'll add this new card where its suit is going to be joker. And the real question here is, do we want to rank? Does it make sense to give it a rank of some sort? So we know in the traditional sense, ranks don't mean anything for jokers. They're all just jokers. But on the off chance that we're playing a game where maybe there's a colored joker and a non-colored joker, or there's something weird with the deck, there are a few games out there, I believe, that do things like that. So what we could do here is just say the rank is equal to the rank. We'll convert I to the rank. And that way, every single joker we add here will have a different value for the rank. And now these aren't technically traditional ranks, but we at least have an integer value there that we can use if we want to differentiate between all the jokers. And then finally, we want to return those cards after our for loop. Okay, so once we've got that written, we might want to test it. So what we could do here is something like cards is going to be new, and then we could say jokers 3, and then we could say for every card in the range of cards, count is going to be 0 if c.suit is equal to joker count plus plus. And then at the very end, we could say if count is not equal to 3, t.error, expected 3 jokers received, and then we could put count. Now we can go test this, and you'll see that it looks like it's passing. We can go ahead and change that to 4 and see what happens. Expecting 3 jokers received 3. Oh, it's because our message doesn't make sense. If we said we were expecting 4 jokers, well, we're clearly not getting 4. Oh, well, that's because this number up here is not 4. So test it again, and we're working again. Okay, so that's, one simple way of testing the jokers. All right, we've got 2 more options to do, and the next one is filtering. So we might want to be able to filter out, for example, 2s, 3s, specific cards. So we want the user to be able to tell us which cards they want to filter. It'd be pretty bad if we gave a filter that only did certain things. So what we're going to do here is create a function. It's called filter, which takes in a filter function. We'll just put an F here. That takes in a card and returns bool. So it's going to return true if it should filter this card, false if it should leave it alone. And then this is going to return us a function that takes in a slice of cards, and will return a slice of cards with everything that returns true for this Boolean or for this function call removed. So we're going to say return func cards card, and then we're going to go ahead here and say var ret, going to be our card slice, and we're actually going to write this a little bit different. Rather than trying to remove cards from our deck, what we're going to do is we're going to go ahead and just build a new slice and only add the cards that don't pass this filter function. So we're going to say for each card in a range of cards, if it doesn't if it doesn't return true from this filter function, then we're going to say ret is append ret with that card. And then at the very end, we'll return ret. And this should be C, not card. Okay, so that's how the filter function works. Now let's go ahead back here and let's add a test. And for this, we're going to want to do something like, maybe we want to filter out all the 2s or all the 2s and 3s. And then for our test, we want to make sure that none of those 2s and 3s are there. So we'll say filter, it's going to be a function that takes in a card, returns a Boolean, and this is going to return card.suit equals 2, or not to suit, we want card.rank equals 2, or card.rank is equal to 3. So that's our filter function. So if it equals 2 or equals 3, we're going to go ahead and return true and say, yes, please filter this. Then we're going to say cards is going to be new. We'll just do a default new deck. Actually, I take that back. We want to call filter with our filter function. And then we want to iterate over all of these. And if c.rank is equal to 2 or c.rank is equal to 3, well, then that means we had an error. So we're going to say t.error expected all 2s and 3s to be filtered out. And now we can go test and verify this is indeed working. Now, if we went back to our code, say for instance, we had a bug where we didn't put the not sign in front of this, we didn't put the bang here. If we ran our code then, you'd see, expected all 2s and 3s to be filtered out. So we're clearly getting failures here. And you're seeing a bunch of these because, I don't mean to do that. It's happening every time it finds a 2 or a 3 inside of that for loop. So that's why we've got 1, 2, 3, 4, 5, 6, 7, 8. So, there's 4 2s and 4 3s, and you're getting this error message for each one of them. So let's fix this up. Make sure we still pass. We're good. Okay, so that's it for filtering. We've got one more, which is decks. That's going to be something that allows us to add extra decks to our, our new deck of cards we're building. And then after that, the two sort of bonus pieces. Originally, the one bonus was going to be just adding documentation to this and seeing how it works with, whenever you run the GoDoc server locally. But I also wanted to add a second little sort of bonus video where I want to talk about ways to sort of test the shuffle function and make it a little bit less random in that sense, to give us a deterministic test. So I'm saving that for the very end to cover that. But for now, we're good with filter. We'll just move on to the next video for adding decks. We want to be able to add new decks to our card, whenever we're generating a new deck. And the primary purpose for this is that we want to easily be able to, maybe we want to build a blackjack deck, and we want to be able to say, okay, I need at least 3 decks here, so I have a lot more cards. So maybe it's a little bit harder for people to count cards than at a blackjack table. So what we're going to do for this is write a function called deck, which is going to take in an integer n, and it's going to return this functional option for us. And this one is going to go ahead and, like before, it's going to return cards, card, and then we return the slice of cards. And what we're going to do here is we're going to go ahead and say, all right, we want to take the deck of cards we have and we want to duplicate it. And I'm going to go ahead and say we're going to duplicate it because we could just take the base deck and add it, but that would just make it really confusing to the user, at least in my opinion, it would make it a little bit confusing. Because they might have a deck that's already filtered, and then if they call deck a little bit later, they're expecting, all that to sort of still be true. So I think this makes sense to do it this way. Now, there's still potential confusion. Maybe they add 4 jokers thinking they're adding 1 for all the decks they have, and then they call deck afterwards, and it's going to duplicate those jokers. So it can be confusing either way, but I think this way is, just duplicate whatever we currently have, and maybe encourage people to call this first if they want to, generate duplicate decks, or, if they want to create duplicates of jokers, just to keep the order in mind. So we're going to say var ret, and this is going to be our card slice that we're going to return, and we're going to return it here in the end. So what we want to do for this is we want to iterate at least n times, do a loop that does n iterations. So we'll say for I is equal to, I'm using like a quieter keyboard because my mechanical keyboard's too loud and it's kind of rough to get used to. Okay, so we've got this loop. Now what we want to do is we want to take whatever's in cards and add it to ret every single time we do this. Well, the simplest way to do that right now is to say ret is equal to append ret with the cards. And that should do the trick for us. Now, this isn't going to be like I'm pretty sure this isn't a deep copy, which basically means that if there were pointers and some nested things down below, I don't see those being copied specifically. It's just still going to be a pointer to the new object. But because our card type is so simple, and it just has this suit and rank, it's actually not going to be an issue for us. So this will actually work very well for what we're doing. So that should be it for the deck. Now we want to test this. So we'll do func test deck. And what we're going to go ahead and do here is just say cards is going to be new. And we'll just say deck 3. So that should give us 3 decks. And that's, okay, I want to make sure we didn't have a bug here. One of the ways you can quickly screw this up is you need to account for the fact that you already have an initial deck. So if you weren't starting with an empty slice here with ret, you wouldn't want to run this n times, you might want to run it n-1. But because we start with an empty slice for ret, we can actually get away with this. Another thing that I do want to mention here is that if you did something like cards equals append cards, this is actually not adding n decks. This is actually doubling your deck every single time. So if you just added 1, put n here as 1, you want to add 1 extra deck. Although technically 1 is still just 1 deck. So if you put a 2 here, what would end up happening is you would end up doubling the deck a couple times, which would not be what you wanted. So, instead of going from 1 deck to 2 deck to 3 decks, you'd be going from 1 deck to 2 decks to 4 decks to 8 decks and, quickly growing to a huge number of decks. So that's not at all what we want. All right, so we got a deck with 3 decks, or we've got a card slice with 3 decks in it. What we want to do next is verify that the length is what we expect it to be. So if the length of cards is not equal to 13 times 4 times 3 decks. So up above, we could put something like 13 ranks times 4 suits times 3 decks. Then we can do t.error, expected, let's do error f, %d cards, received, %d cards. So we can do 13 times 4 times 3 is what we expected, and the length of cards is what we received. Go ahead and save that, get rid of that extra line at the end, and then go test. And this appears to be working for us. Now, if we went back here to our cards, again, I'm going to show you what I meant by that. If you didn't add this ret, and you instead did cards equals append, cards, and returned cards at the end. You'll see here now when we do this, expected 156 cards, received 416. So that's way off from what we expected. And that's because it's doubling the cards every time it does that rather than, just adding new decks. So let's go ahead and change this all back. And we are good to go there. Okay, so that's it for the core part of this stuff. I'm going to try to add the bonus stuff here in the next couple of days, but I wanted to go ahead and get this stuff out. So I'm going to go ahead and ship this as is, and then you should see some new videos added over time. But this will give us a pretty good foundation to work from as we go ahead and build the blackjack game and, add our cards to it and everything. Now, there's probably some things that could be improved here. I haven't given this a ton of thought. I've also not used it a ton. I toyed around with what I think the blackjack game is going to be, but I haven't actually, coded everything perfectly and coded a bunch of other card games. So there definitely could be some ways that we might want to change this down the road. And, that's one of the reasons why, generally speaking, designing a package like this without actually having a use case for it is a bad idea, because you won't really understand the use case unless you have one that you're going to use. But in this case, I think it's okay. We're still teaching a bunch of things here, and it's sort of an experimental thing, so I think it's fine for that type of exercise. To start the bonus stuff, we're going to focus on testing this shuffle function up here. And what I want to say is that if we tested this as it is, it's not that we can't write code to try to test it. It's that it's really hard to come up with any specific assertions. For instance, if we say the first card should not be the ace of, spades is the default. Well, there's always that slight chance that when it gets shuffled, the ace of spades is still the first card. Otherwise, it wouldn't be a real shuffle. If one of those specific permutations wasn't possible, it's not a true shuffle. So we don't want to do that. We don't have a test that can sometimes fail. And that's the big thing that you'll run into with any test that use time or random and things like that, is that you really don't want these tests that can sometimes fail, but still, it's not really a failure. If a test fails, you generally want it to mean something's wrong with the code. Otherwise, people start to ignore the tests, and then when you do actually have bugs, people don't really pay attention to them as much, and it can be really problematic. So what we're going to do here is we're going to look at how do we make this function here, deterministic, something that we can know every time we run it exactly what the output's going to be, while still allowing us to get random permutations. So one of the ways you can do this is to have this function accept a random source. So we could say shuffle now becomes a function that takes in a ran.source, and it returns a function that takes in these cards and does all that. So then we could say return func cards, card, like this. And it ends up being very similar to a lot of the other stuff we have. We just end up doing all of this, and then instead of doing all the other stuff, is this supposed to be, I think it needs to be a pointer? Not really sure what we're complaining about here. Nope, ran.source is an interface. Let me go ahead and check. Oh, it returns a ran.rand. Is that right? Okay. So you could do something like this, where you accept the ran.rand, and you go ahead and call perm from that. You could accept the source, like I had said, and you could say we'd make this S up here for source, r : ran.new, with the source that was passed in. And that would work as well. So we've got, two different ways to do it. Somebody can either pass in a source, or they could pass in, say, the actual random part that generates this perm. We could also even provide our own interface. So we could do type permer, which is, sounds weird, but that's okay. And it could have a function, which is perm, which takes in an integer and returns a integer slice. I think that's what we have here. So we could say permer or p permer, and then down here we could just say p.perm, and this code still works. So we've got all of that. We've got 3 different options there for that. What I don't love about this is that as an end user, using this sucks. It's not that it sucks terribly. I mean, you can pass in some sort of permutation thing. You can do your own random sourcing, and it gives you some flexibility as an end user. But the truth is, most of the time when somebody's using this, they want to write code that's something like, new deck, shuffle it, and, I'm off on my way with a shuffled deck of cards, doing whatever I want to do with them. They don't really want to do something like new, shuffle, and then here they got to think, okay, how do I create a permer? All right, I need to do r.new, and then I need to do r.new source, or not r, I want rand, new rand.new source, and then I need to pass in time.now.unix, and this ends up being much uglier. It's not really clear what all this is, what it's there for, anything like that, and a lot of times people just don't care. They're like, just give me a random shuffle. As long as it's reasonable, that's fine for what I'm doing. Now, if you're running a casino, you might care a lot more, but, for what we're doing, I don't think that matters. So what I think we're going to do here is we're going to look at other options. And what I think we're going to do is, instead of having this passed in here, I'm going to go ahead and change this back to take the cards as an argument. It's not going to return a closure anymore. It's just going to be a function that is an option. And I think what I'm going to do instead is just put, do rand, or we'll do shuffle rand, is going to be rand.new, rand.source, something like this. Now we can take shuffle rand, and inside of here, we can call perm on it. And I want new source. Yeah, okay. So this all works, and we can use it, but it still doesn't really make testing that much better. When we look here, testing is really not any better because we're still getting random numbers. So it's not really ideally what we want. The other thing that kind of isn't amazing about this is that we've got this global or this package level variable that is available to the entire package. Now, we're not exporting it, so it's not terrible, but if you can avoid package level variables, a lot of the times it'll make your code easier to use and better, especially if it's things like this, because something that could happen is another function up here might modify this without you realizing it, and it could change the behavior of your code and cause an issue. Specifically, if we have tests, maybe they modify this slightly and another one expects it to be something different, so that could cause an issue. But in this case, it's only being used here, so I think it's fine to leave it there. It's going to make our API a little bit easier to use. Long term, we might want to add a second option with a shuffle with source or something like that, so we have a little bit more flexibility. But I think for now, this will be fine. And what we're going to do for testing is, instead of using this value of rand, this one that actually has a source that's random, what we're instead going to do is we're going to create a new random that has a seed that we know about, so we'll always have the same results. So let me go ahead and show you. I can probably do it in the Go playground. One of the things that's cool about rand is that you can say r is going to be rand.new source 0. If we do r.perm of 5, and we print it, let's go ahead and get imports and run this. And you'll see that every time I run this, it's always the same result. If I change my source to be 1, the results change, but they're always going to be the same results. So the source dictates every time you call r.perm, it's going to use that source as a seed for the random number generator. Now, if we call it 3 different times, it won't have the same value all 3 times, but the first one will always be the same, the second one will always be the same, the third one will always be the same. And that's why whenever we're actually seeding this random, we always use the current time, down to the Unix, with time.now.unix, because that gives us a time that is going to be relatively random enough, because the program's being run at different times every time, that it should seed our code and give us relatively random results. But if we wanted to test it and we wanted to verify it's in a specific order, you can actually seed it with a specific value, and then you'll know for certain, what order to expect everything in. So to do that, we're actually going to do a new source here. And let's say we're expecting 52 cards to be in our deck. So we're expecting it to call r.perm on 52. If we run this, you'll see this is the slice that we're expecting. So we're expecting whatever card was at 40 to be the new card, that's at the first index. Whatever card was at 35 to be at the second index. So knowing that, let me go ahead and copy this. And we're going to go here and we're going to add I don't want it sort. I'm going to do func test shuffle. And we're going to say shuffle rand equals rand.new, rand.source, new source, 0. So we've essentially overwritten the shuffle rand that's inside of that package. And once we've done that, we know that we should get, make shuffle rand deterministic. So the first call to shuffle rand.perm 52 should be, and we don't actually need all of these. I'm going to go ahead and do this. All right, so that's basically describing what's going on here. The first call to shuffle rand.perm with length of 52 should give us something like this. So with that, what we can go ahead and then do is say cards is going to be new shuffle, and we know a new deck has 52 cards. We know when we call shuffle with it that it should go ahead and shuffle those cards with 40 as the first number. So now we need to know, all right, what's the normal card that's at 40, index 40? Well, the simplest way to do that is just to create a new deck. So we'll say sorted, or just say original deck. And then we can say first should be orig 40. And then we can say second should be orig 35. And then once we've gotten all that data set up, we can go ahead and do cards equals new with the shuffle. And then from there, we can say if cards 0 is not equal to first, or cards, well, we can just go ahead and do it this way. Expected the first card to be %s, received %s. And then we'll say first and card 0. And this needs to be t.arrf. And then we're going to go ahead and just copy all of this, paste it, make that a 1, make that second, and do the same thing up here to change all this. And this should give us a relatively deterministic test. I think it's govet that's complaining here because I'm passing in these cards, but I think they'll still be fine. And I need to check out a new part. So go test seems to be passing, but I want to go ahead and just say what happens if we get an error. All right, so you'll see here, expected the first card to be 10 of clubs, received 10 of clubs. Well, that's because I have this as second still. And it's complaining because I don't use this. All right, so we're expecting the first card to be 2 of hearts, received 10 of clubs. So that's what you're seeing here. If we have a bug down here, this is actually a bug in our test, not in our code, but you're seeing here that that's what we'd see if our shuffle function was broken for some reason. So I'm going to go ahead and change these both back to second. And you can see here now that our code has a deterministic test because we are seeding this random specifically with a value that we know the result from. And sort of setting that all up, it's not awesome to have to set all of that up and sort of depend on all of that stuff happening in that exact order. But it's better, in my opinion, than coming up with a test that, instead of doing all this stuff, the test ends up doing something, it ends up doing something that could fail later on. It ends up not being something you can test deterministically. Now, there might be other approaches to that as well. For instance, another thing you could do is you could maybe build 3 or 4 decks, shuffle them, and as long as all 4 of those decks have a different order, you can assume your shuffle is working. So that is a valid way to go about doing it. It really just depends on how positive you need to be that certain things are working and, what your risk model is and different stuff like that. So I don't want you to feel like you have to go about doing it this way, but I do want you to see that there are options as far as when you write your tests to set them up in a way that you aren't forced to just, write tests that could potentially fail at some point. You can actually write things that, shouldn't ever fail.